these examples. So I'm only going to do 3 examples with you. Guys, another 20 seconds here, and I'll assume that we're ready to go, and then I'll start our first example. Okay. Only other thing I'll say before I start these examples are, these are all word problems, right? Related rates are always word problems. I'm not going to give you guys a bunch of time to write the word problem down. I'm just going to ask that if you don't have the guided notes printed out, just go back later in class and actually write the full question out yourself if you need to in your notes. But I'm really just going to try and focus on how to set the problem up and how to solve the problem, and let you go back on your own time to write the actual word problem out if you need to. Okay. All right. The first one is a ladder problem, because there were some questions about this one on the homework. It says a ladder is 20 feet long leaning against the building. Okay. Whenever you see these ladder problems, usually they relate to triangles and Pythagorean theorem. So let's start to draw this out. You've got a ladder leaning against a building. Okay, let's call that a right triangle. Now this ladder is 20 feet long. Okay, so we're going to start to label. We've got a right triangle here, so I'm going to label A, I'm going to label B, I'm going to label C. Okay, now this ladder, it says, is 20 feet long, so the ladder itself is 20 feet. So it looks like this side of the triangle is going to be 20 feet. Okay. Let's see what else they give us. If the bottom of the ladder slides away from the building horizontally at a rate of 4 feet per second. Okay, so what it's telling us is the base of this ladder is being pushed out from under it. Okay, so that's a rate of change. 4 feet per second is a rate of change. So I'm going to call that dA dt. And since that leg is getting longer, it's going to be a positive 4 feet per second. Okay. Now it says, how fast is the ladder sliding down the house? Okay, so this ladder, the leg is being kicked out, so it means this top part is being slid down the house. When the top of the ladder is 8 feet from the ground, so at the instant that this leg length is 8 feet, how fast is the ladder sliding down the house? Well, that's a rate of change, right? How fast something is changing. That would be dB dt. Okay, and I'm keeping an eye on the chat screen, guys. If there's any questions as I'm doing this, just feel free to type in and I'll pause and answer it. Okay, so how fast is this sliding down the house? So we have a right triangle. This is going to be Pythagorean theorem, a squared plus b squared equals c squared. Okay, this was really step 1 of the notes that you guys wrote on our last class period. Step 1 was always draw a picture and figure out what geometric equation you were doing. So this is step 1. Okay, if I look at this picture and I look at this equation, it looks like I'm missing a few things. I'm obviously missing dB dt. That's what I'm solving for, so I'm not going to have that. But if I'm solving for dB dt, that means I need everything else. So first we're missing this length, okay? To get that length, we can go back to the Pythagorean equation and solve for it, because we have a C and we have a B. So to solve for A, okay, when you do that, it's going to be 20 squared minus 8 squared. You take the square root of that. It's actually going to give you a pretty crazy decimal, so I'm going to leave it as a square root to start. This would actually be square root of 336. I'm going to put that right over here, square root of 336. I'm not seeing any questions so far, so I'm going to assume I'm safe to move on. So again, back to this question, how fast is the ladder sliding down the house? Well, if we want to find that rate of change, we're going to have to find the derivative of both sides of the equation, implicit differentiation. So let's do that down here. I'm going to take the derivative of the left side, and it's going to be 2a. Now it's changing with respect to time. So remember, I always have to write the dA dt after it. Plus 2b dB dt equals, when I do this, I have to take the derivative of both sides. So this would be 2c dc dt. All right, whenever I write the equation out, I like to just go back and say, what do I have? What am I missing? I have an A. I have a dA dt. I have a B. dB dt is what I'm solving for. I have a C. dC dt. This is the one that I got a lot of questions on the homework. How do you find dC dt? Okay. If the ladder is sliding down the house, it doesn't tell us in the problem that the ladder is changing size. We are not folding up the ladder. We're not extending the ladder. The ladder is simply sliding down the house. So there is no change in length of that ladder. The only thing that changes is like the angle that it's leaning against the house. So if there's no change in length of the ladder, your dC dt is going to be 0, and that's going to zero out this whole side of the equation. Okay? All right, so we're solving for dB dt, and at this point we have everything. It's just reworking the numbers here. So I'm going to say 2b dB dt is equal to negative 2a dA dt. And I just want to divide out my 2b. When I plug everything in, dB dt is equal to, what do we have here? Negative 2, what is a? Square root of 336. dA dt is 4 all over 2 times 8. It would make sense that you're going to get a negative number because it's sliding down the wall, right? That leg is getting smaller. So I'm going to say my dB dt. I know there's a question right now in the chat, so I'm going to check that in 1 second. dB dt would come out to, let's round here. So let's round to 3 decimal places, negative 9.165, and we are in feet per second. Okay, question, why did the right side of the equation with 2c cancel out? It's because when I took the derivative of this side, c squared, it became 2c dc dt. Well, we talked about how the ladder is not changing size, or it's not changing size. So dc dt is 0. So anything times 0 is 0. So it just zeroes out that whole side. Okay, thanks for that question. Hopefully that answered it. Okay, before we go on to our next one, I am having a ton of problem with my smartboard today, and I can already tell that it's starting to die on me right now. If for some reason it starts messing with me and messing up on this next example or two, I'm just going to switch this to a document cam. You just have to be patient so I have a chance to set it up. But let's see if we can at least get through this one. Um, okay, similar type of problem, but there is definitely something different you're gonna have to do on this that we haven't done before. Sonia and Isaac are in motorboats located at the center of a lake at time t equals 0. So now we're introducing time. Sonia begins traveling south at a speed of 32 miles per hour. That's a rate of change. Miles per hour, you're changing. At the same time, Isaac takes off heading east at a speed of 27 miles per hour. That's another rate of change. And then it says, what's the rate of the distance between them increasing at t equals 12 minutes? Okay, let's draw this. We're starting at one spot and she's heading south at a rate of, I can't see it on mine, so let's look at this, 32 miles per hour. So first let's draw the picture first. And he's headed east, okay? So you've got these boats heading in different directions. And the question is, at what rate is the distance between them increasing at a certain time? So they're asking, what is the rate of change of this distance between the two boats changing? Okay, so I have a little right triangle there. So let's go back to labeling A's, B's, and C's. Let's call that A, let's call this B, and let's call this C. Now be careful because all they're giving you is rates of change. She is driving at a rate, dt, of 32 miles per hour. That's a rate of change, miles per hour. He is driving at a rate, it's not going to be B, it's going to be dB dt at a rate of 27. These are both going to be positive numbers because they're moving outward. The legs are getting bigger. Okay. So the problem here is, if you were to set up your equation, you're missing a whole lot of stuff here. You're missing A, you're missing B, you're missing C, and actually it's asking you for, it wants you to solve for dc dt, right? That's what the question's ultimately asking for. So we got through step one, we drew the picture and we have our equation, but we have a lot of missing pieces. If you come across something like this, always look back at the problem and say, is there information they're giving me that I could use here, okay? One thing that we introduced in this problem was time, okay? Time is 12 minutes. Now, before I do anything, I wanna make sure that my units are all the same. This is miles per hour, this is miles per hour, but this is in minutes. Let's make sure they're all in the same unit. So let's make sure it's in hours. So this time, I know I'm kind of running out of room here, but this time is actually 0.2 hours. So now I have everything in hours. Why does that help us? Because we can use that time to get our instantaneous values at that time, A, B, and C, okay? So to find A, if I'm going 32 miles an hour, she's going 32 miles an hour, after 12 minutes, which is 0.2 hours, you would say right here, you would say 32 times 0.2, because that's the instant that you're evaluating. Okay, 32 miles per hour after 12 minutes, and you would come out with 6.4. So at that instant, after 12 minutes, your A is 6.4. Okay, I'm going to do the same thing for B. I would do 27. I know I don't have much room here, but it would be 27 times 0.2 if you're writing this in your notes. That would come out to 5.4. Okay, I'm not seeing anything in the chat, so I'm probably safe to go on. How do we find C now? So I don't have a dc/dt, so I can't do the same thing for C. But what I do have is an A and a B. Now I can find C. Okay, so if I just take the square root of both sides here, it should be 6.4 squared plus 5.4 squared equals square root of c squared. C would actually come out to 8.4. At this point, it is the same type of problem that we just did in our last example. Now it's just a matter of taking the derivatives of both sides, finding your dc dt, and going from there. The only difference in this problem was at the start, you had to use that extra time information to find your A, your B, and your C. Okay, so just to keep working through this, take the derivative of both sides, 2a dA dt plus 2b dB dt equals 2c dC dt. I'm going to go back and double check. I have A, I have dA dt, I have B, I have dB dt, I have C. All right, this is good. That means that's the only thing I'm looking for right there. Okay. To save you guys a little time working through your calculator, this comes out to 409.6 plus 291.6 equals 16.8 dC dt. And I'm losing my smartboard. Anyway, you want to add those up and divide. I'll let you guys do that. I need to fix my smartboard here to see if this is going to work. Okay, anyway, your final answer on that should be 41.7, and it looks like that's miles per hour. That's the rate of change, miles per hour. Okay, we got one more example. Is there any questions? Okay. Yeah, definitely don't wait till you get in work time, or don't wait till you get in a breakout room to think, oh my God, I really don't understand any of this. Please ask questions if you do have questions. That's what I'm here for. Okay. All right, last one. I'm hoping my smartboard can stick with us for one more example. And this is something completely different from what we've done before. We're not going to use Pythagorean, but it's still a triangle. It says that a balloon rises at a rate of 4 meters per second from a point on the ground 50 meters from an observer. Okay, so let's draw that. Okay, you've got this balloon that's rising, and you've got this observer that's 50 meters away. Okay, so this observer, let's say it's like they're standing right over here. Find the rate of change of the angle of elevation. So this is brand new. We've never talked about angles before. Rate of change of angle of elevation of the balloon from the observer when the balloon is 50 meters above the ground. Okay, so this observer is looking up at this balloon at a certain angle. Okay, what we do have is, I'm going to call this my x-axis because I'm horizontal. We do know that that observer is standing 50. Let me circle it here for you. 50 meters from an observer. Okay, so we know that this is 50 meters. We also know that the balloon at this instant is 50 meters above the ground. Okay, and it's asking us for the rate of change of the angle of elevation. Okay, what does that mean? Angle of elevation. So your theta, your rate of change of your angle is going to be d theta dt. Okay, that's what it means by rate of change of angle of elevation. So that's essentially what we're looking for in this problem. Okay, you're not going to use Pythagorean theorem. It has nothing to do with side lengths or what is the distance between the observer and the balloon. Doesn't have anything to do with distance. It has to do with rate of change of angles. So if you think back to our slide last class period when we had like those common equations, we said area of a circle, we talked about Pythagorean theorem. We also talked about SOHCAHTOA, sine, cosine, tangent. As you're looking at this, you have a y, you have an x, and you want to work backwards to get this rate of change of angle. I just want to see in the chat, what trig function could I use here? Could I use, based on what I'm given, could I use sine? Could I use cosine? Or could I use tangent? Good. All right. Good. Okay. A lot of people saying tangent. Think of SOHCAHTOA. Sine is opposite over hypotenuse. Well, if you did opposite over hypotenuse, you have, here's your angle. Opposite is 50. You don't want to know anything about the hypotenuse. You don't need that. Cosine is adjacent over hypotenuse. Again, here's your adjacent. Hypotenuse is over here. You don't have any information about your hypotenuse. Tangent is opposite over adjacent. You have your opposite. You have your adjacent. You can use tangent to work backwards to get to this angle. So actually the equation you'd be using is tangent theta equals y over x. That's the geometric equation you'd want to use for this one. Okay. All right. Couple things. We have a y, we have an x. What we don't have right now is a theta. Okay. You can work backwards, and I'm talking about this theta right here. You can work backwards to get that. If you remember from whether it's pre-calc or algebra 2, to work backwards to get that angle, if you were to say tangent inverse of y over x, so 50 over 50, so basically tangent inverse of 1, you would want to, well, a couple things. You want to make sure that your calculator is in radians, okay? Because in calculus, we're always in radians. Tangent inverse of 1, you really kind of have to know the unit circle for this. We know that tangent is y over x. Think of the unit circle. Think of pi over 6, pi over 4, pi over 3. If you do y over x, square root of 2 over 2 over square root of 2 over 2, this would become pi over 4. Okay, so tangent inverse of 1 becomes pi over 4. And again, there's really no way around that other than just looking at the unit circle or knowing the unit circle and saying, okay, when I divide y by x on those unit circle coordinates, which one would give me a 1? Okay, and it would be pi over 4. So now you have your angle. It's going to be pi over 4. Okay. All right. So let's go back. We have everything we need. We've got theta, we've got y, we've got x. The only thing we're looking for is the theta dt. So I'm back to this equation, okay? And I'd want to take the derivative of both sides, okay? You could take the derivative of both sides like this, and then on this side, you'd have to use the quotient rule. A lot of times, people would prefer the product rule because that goes a little quicker than the quotient rule. You can rewrite this equation to be x tan theta equals y. Okay, all I did was just bring the x right over here. The reason I did that is because now it's going to be a little bit easier to take the derivative. I've got the product rule right here, and I've got y over here. So I can take, it's just a little bit easier to take the derivative of both sides when you're not dividing anything. Okay. When you do that, this is first, this is second. So let's say first derivative of the second plus second derivative of the first. So if I were to take my derivative, I would have x. Actually, let me back up 1 second. You could work through the product rule here, but I just noticed that another shortcut would just be knowing that your x does not change. Okay, your x is always 50. Nothing's changing on x. So I could rewrite this as 50 tangent theta equals y. Again, you could do the product rule. You could do all this stuff in red that we were talking about. You're going to get the same answer. But all I did here was I just made this a constant, okay? Because I know that it's always going to be 50. Okay, that way I don't even have to use the product rule. Okay, so this, now I can take the derivative of both sides. That stays 50. Derivative of tangent is secant squared theta. This is where you get the d theta dt. Because when you take the derivative of tangent theta, you get secant squared theta d theta dt. And on this side, you've got your dy dt. I'm going to check my chat box. I know I've got one question up here. Good question. Why is y also not 50 for the equation? It's because, let me see. Oh, it's because your y, so your observer is not changing distance. So your observer is standing 50 meters away. However, this balloon is rising, okay? So at that instant, it's 50, but it's still rising. And actually, I missed a piece here. This was dy dt. And it says at the very beginning of the problem, in that first sentence, a balloon rises at 4 meters per second. So I missed the dy dt there is 4. The reason that the x stays constant and not the y is because the balloon is moving upward, whereas the observer is standing in one spot right here. Okay? If they're standing in one spot and they're not moving and there is no dx dt, then you keep your x the way it is. The y is the thing that's changing, so that's why that's not just going to be a constant at 50. And we can, either way, the y goes away here because we take the derivative of it and becomes dy dt. Okay, another question, wouldn't it be x secant squared? What happened to the tan theta? Okay, so there's a question on what happened to the tan theta here. So on, let's just say, for example, I did use the product rule there. Okay, you would have had, and I'm just going to do that underneath here. You would have had first derivative of the second plus second derivative of the first, which is just 1. So then that would become, yeah, you're right, this would be x secant squared theta d theta dt plus tangent theta equals dy dt equals let me think about this. I think it has to do with the 50 being constant. So if you have the 50 as constant, first derivative of the second plus second derivative of the first. I gotcha. Yeah, that's a good question, Alyssa. It looks like you would have to, it looks like you can't use either or. Because if you use the product rule like I have down here and like you did, or like you stated here, you would get a different answer. So I think the key here is, and let me go back to this top part up here where x is 50. I think the key is leaving that as your constant because the x doesn't change at all. I think when you get into the product rule, the reason that it's coming out differently is because you're not treating an x as a constant. You would end up taking the derivative of the x, which would become 1. Actually, here's where it would happen. The derivative of x. All right, I got it now. This is why it would be the same. So now we have x secant squared d theta dt, and this would be tangent no, I'm losing my board. Hang on with me like one minute, guys. Let me fix this, but I've got your answer here, Alyssa, I promise. Okay, so this was first derivative of the second plus second derivative of the first. Okay, this is why it becomes the same, because the derivative of the first, so the derivative of x becomes dx dt, and that's all equal to dy dt. Okay, so let me rewrite this out. I had secant squared d theta dt plus, so again, go back to this. You have x secant squared theta. So first derivative of the second plus second derivative of the first. The derivative of x with respect to time is dx dt. I know we're used to, up until this point, we're used to just taking the derivative of x because it's always looking like this. It's always dx of x, and that's always going to be 1. However, in all of these related rates problems, we are taking the derivative with respect to time. So this just becomes dx dt, okay? When that happens, dx dt, since we said it is not changing up here, the dx dt becomes 0 and it goes away. So that's how they end up the same. The dx dt is 0 because the observer is not moving and it's the same. I know that was a long-winded explanation. Does that help at all? Okay. Thanks, Alyssa. And I apologize for that long-winded explanation. I just had to make sure I was explaining that right. All right. Let me get rid of this. Okay, we are solving for d theta dt, so we are one step away here. This is going to become, so let's write d theta dt is equal to dy dt over 50 secant squared theta. Okay, I'm pretty sure we have everything here. We have our dy dt, right? That's going to be 4. 50 is our constant. Secant, let's change that to cosine because that's going to help us use our calculators. So I'm going to say d theta dt is equal to, now this is technically, secant squared is technically 1 over cosine squared. Okay, if I were to flip that, multiply by the reciprocal, make more room here, d theta dt. If I were to multiply by the reciprocal, just bring that up top, it would be dy dt cosine squared theta over 50. Okay, at this point, you just plug everything in. The dy dt is 4, so d theta dt is equal to 4. Now you have cosine squared pi over 4 over 50. Okay, you could, and at this point, you don't necessarily have to know the unit circle to do cosine squared pi over 4. You could really do the whole right side of that equation in your calculator as long as it's in radians. You should be getting d theta dt is equal to 0.04 radians per second.